Okay, can you do?
Yeah. Good morning.
¿Están? It doesn't matter actually.
Se escuchó una voz, pero no.
As you can see here, this is the straight plate turbine creating radial motion within the fluids. But on the other hand, this is the paddle impeller, which creates the axial flow. So what I've used in my project, the first one, which is the varying blender mixer, which is recommended by API for preparing fluid in the laboratory. It contains around 600 milliliter of slurry, and with an adjustable rotating impeller, which is the high efficiency blade type. So how you prepare the cement based off API recommendation? I use Class G cement, which should be 44% by weight of cement mixed with water. You have 15 seconds to add cement to the slurry while it's being mixed at 4,000 RPM. And then you let it mix for another 35 seconds at 12,000 RPM. This is the RPM, 12,000, and this is the 50 seconds should be mixed in total. And then I have also used an intermediate mixer, which also with adjustable rotating speed and adjustable volume. You could use any kind of bucket you want to mix, so you can adjust your volume with your purpose. The next one was the big batch mixer with an anchor type impeller, rotating at fixed rate of 70 RPM. And yeah, here is a video. So if you compare it with the previous one, you had some kind of vortex-shaped fluid in API mixer, but here it's comparably smooth surface with no vortexes, not much turbulence. So that's pretty much different. So, yeah, as I said before, it's very important in any design that we should have a criteria to scaling up different procedures. And also the scaled up procedure should be representative of the lab mixing or anything you're doing in the lab. A well-known way to make this synergy between different scales is dimensionless analysis, which I will talk about in next slides. And by the way, scaling up is not just multiplying all parameters by a single factor. It doesn't work like that. Some earlier studies have proposed that concept of specific mixing energy, SME, as a good tool for making this synergy between different scales. Specific mixing energy is literally the amount of mechanical work you are putting into the mixed slurry. So it's been first announced by Orban and Gouliot in 1986 for compare different slurries being mixed at different scales. There are some studies in the literature from 90s that saying this concept is sufficient to be followed. For example, if you have the same specific mixing energy for any mixing process, you will get same properties for the final product. A guy named Paget also added something to that concept, which was shear rate. He said that the energy itself is not sufficient enough, so we had also considered the shear rate we are mixing the cement at. But more recent studies claim that this concept is not good at all. It doesn't reflect all properties of the cement. For example, free fluid, the UCS, and other stuff. This is the earlier correlation for the specific mixing energy. This K is the constant experimentally found. This is omega rotational speed, time, and volume. And this one is the Paget guy suggested relation, which has the shear rate in it. So what I've done is I want just to test this concept. If SME is good enough to scale the mixing process or not. So I prepared different slurries using Class G cement with 3 different mixers I showed you earlier. And then I measured the properties, both the slurry and the hardened cement, and compared to each other. As expected, the primary results show that the SME is not good as it used to be, or they used to say. So we needed to come up with another solution. This is a slurry behavior of the fluid that was prepared at same SME, but with different mixers, one with API and one with batch mixers. As you can see, there are pretty much big difference between it. There are also big difference between the other properties of the cement as well, like UCS strengths, porosity, gel strengths, and free fluid. The percentages shows the variance of the data. So, okay, SME is not working. So what should we do? How should we make the synergy between these different procedures and different mixers? How should we be sure that the cement we are making in the lab will represent the cement in the field, or vice versa? A well-known analysis method for this is Buckingham-Pi theorem. Most of you might remember from your fluid dynamic course if you take that, but let's refresh our minds about this theorem. How does it work? With an example. So, yeah, consider I'm working for a company and my boss asks me, okay, Payam, find the drag force on a smooth cylinder in a wind tunnel. I said, okay. First, I have to find out the dependent variables. So drag force is dependent on the diameter of the cylinder. Yes, of course. The velocity of the fluid. Yeah. In a moving car, you put your hand out of the window. The faster car goes, the more force you feel on your hand. So velocity is here. Density, viscosity. Yeah. If you are moving in the air or in the water, that would matter. Okay. Now I find the variables. Now I have to do tests, experiments, to find the relation between these parameters. So first, I measure drag force at different diameters, at different velocities. Okay. I repeat this at different velocities, but at a single viscosity and density. I have to repeat these at different viscosities, all these tons of tests, different densities and velocities. So consider you have done 10 different values for each. Each test takes, I don't know, an hour, and you work 8 hours a day. It will take 3 years to perform all these tests, right? But in the meantime, my boss also asked another guy the same question. But he, instead of doing all these different variables and measuring drag force, he just figured this 2 parameters. He started with a diameter and measured data. Okay. Next, velocity, different viscosity, different density. Oh, I realized that, okay, no matter how I change the parameters, they are all on a single line. So he discovered something. But instead of doing tons of experiments for 3 years, he did it in 2 days or a week, maybe, with single figure. The question is how he found these parameters, right? And that's where the Buckingham-Pi theorem comes in. So there are a step-by-step procedure in this theorem. First, you write the functional relation, which we did, okay? And then you select repeating variables. In these variables, you shouldn't select the dependent variable, which is here drag force. You could choose 3 of any of these. So I choose rho VD. So we have 5 variables, 1, 2, 3, 4, 5. Number of fundamental variables. In Buckingham-Pi theorem, there are 2 series of fundamental variables. It's either force length time or mass length time. So I use mass length time system, which we have 3 fundamental variables here. So the final pi parameters we will get is by getting 3 out of 5, so it's 2 pi group we will have at the end. So how it works, we write pi1 equals to the repeating variables we chose here, v rho d multiplied by the other remaining variable, which for the first one is the drag force. The aim is make this equation unitless, dimensionless. So you write each unit of each parameter. Velocity is meter over seconds, length over time, rho, mass over cubic length, d is length, and drag force is mass length over t squared. So to this equation to be dimensionless, the summation of these powers should be 0, right? So we don't have any unit for the equation. So by substituting this and solving the equation, we will get A, B, and C. And so the final parameter for pi1 would be this, which was this one, right? So we would have 2 pi groups. So for pi2, we repeat the procedure, but instead of drag force, we put the other remaining parameter, which is viscosity here. And then we repeat all tests, and we get this parameter, which is inverse of Reynolds number. Again, this one. So the pi theorem makes life very much easier. Instead of spending 3 years on doing experiments, spend a lot of time and resources and effort, you just do it in a single test or very handful tests. So you get better results. For the first one, you just did it for 10 different parameters, but this figure works for anyone, or anything, any parameter. So I use the same procedure for my tests. So I wanted to measure the power consumed during the mixing. So what would be that dependent on? It would depend on the mixing speed, of course, the diameter of the plate or impeller, the mixing time, volume of the slurry, viscosity, and density of the slurry. So I chose N, rho, and D as my repeating variables. I have 7 variables, 3 fundamental variables, so I will have 4 pi groups, right? Just follow the same procedure here, and my first pi is P over rho N 3 D to the power 5, and this is called power number. It's a dimensionless number, and it's been called power number. Pi 2 again, and this one is also again Reynolds number, inverse Reynolds number. Pi 3, we got this one, and I call this dimensionless mixing time. And at the end, for the volume as the remaining parameter, and we get this dimensionless volume, which represents the geometrically similarity between different scales. So I got these for dimensionless numbers. So we know that the power number is a function of Reynolds number, dimensionless mixing time, and dimensionless volume. In my analysis, instead of keeping SME same, I tried to keep these dimensionless numbers same to see if I get same results for different mixers. So for different slurries, I tried to keep power number, Reynolds number, and dimensionless mixing time same for different slurries. being mixed at different rates and with different mixers. And here are the results. Although the mixers were different, but we have pretty much same results for the slurry. Here we have same geometry and same dimensionless numbers. Here, from the first case, which we had same SME, but different geometry, different values for cement. Same geometry, different dimensionless numbers, same SME, still different numbers. But same dimensionless numbers, same geometry, same values. So no matter how, with which equipment you are mixed, since you keep these dimensionless numbers and the geometry same, you will get same results for your slurry. Either it's cage mixer or API mixer. So, as a result, these tests were carried out with 3 different mixers at 3 different geometries, 3 different volumes. So 2 of these mixers were geometrically similar. If you recall the dimensionless volume, they had the same number for that. And we saw that if you keep these numbers same, and if the mixers are geometrically similar, you will get same product for your cement. So, all in all, mixing a well cement is really a complex process, which requires a lot of research and resources to spend on. And based on our observation, we concluded the variation of the cement slurry properties such as rheology, strengths, free fluid, porosity will affected by how you mix it. And yeah, and at the end we claim that if you keep these dimensionless numbers instead of the mixing energy concept same, you will get the same product at the end. So thank you for your attention. We will run a Kahoot quiz, but if you do want to run it now or after questions and comments, if any.
After questions and comments.
Yeah, okay. Yes. So feel free to ask anything you want to.
Yeah. In your presentation, you say there needs to be done more research. Like, which are the directions to research in? If you do research regarding cementation, which are the possible directions for students like to focus in?
Yes, in my tests, I used these mixers that were geometrically similar. So one way could be that if you change the mixer type or the blade type, impeller type, what would that affect the mixing? That would be one possible way to go. Yeah. Yeah. Okay, if there's no other questions, we can begin the Kahoot. Yeah.
Talk about how cement mixing can affect the actual results in the end.
Mm-hmm.
But what about the downhole conditions that are affecting? For example, if it's a abnormally pressured well, so how will that be affecting?
Yeah, that's a whole other story.
Mm-hmm.
In this research, I try to make sure we are making the cement we are making in the field is the cement we are making in the lab. We have the same properties for both. Okay, so if you make sure of that, you can test downhole condition in the lab on the cement you prepared. So and you can expect same results in the downhole conditions in the field.
Could you please probably, it was mentioned you give the composition of the cement, some observation. Is it like well-based cement or?
It's Class G Portland cement that I use, yeah, which is very common.
And are you planning in your research to change the chemistry?
No, I didn't, but that could be a possible way to try with different chemistry, different combinations. Also, I used neat Class G. You can also add additives, dispensers, or raking additives, this kind of stuff. I didn't use any of it.
Class G cement is ordinary.
Yeah.
Portland cement.
Yes. Yeah.
With high calcium content.
Yeah. And it's very common in Norwegian. Sure. Okay. Okay, let's start Kahoot. And I have to say there's a price for the first person, which is this drilling data handbook, pretty much expensive book. So it would get handy for the winner. Okay. You have Kahoots on your cell phones? Yeah. So you could use the time to install it. Okay, now you can join with that thing. So by the way, all of you are master students, or is there any bachelor? No? Could you type the pin for the game? And I think the online participants are the employees, so they won't.
No, there are a couple of students.
Okay. Okay. Are you ready? Let's begin. Which of the following is not a roll of cement in a well? Three seconds. Nice. Which of the following cement properties are not affected by mixing process? Viscosity, density, porosity, strength. Yes, strength. Who choose that? Okay. Nice. Which kind of impeller are most proper to mix high viscosity liquids? High efficiency blades, straight turbine blades, three-blade propeller, anchor, helical anchor, and helical ribbon. In API recommended procedure of mixing cement, how long does it take to mix a slurry in total? 50 seconds, 60 seconds, 35 seconds, 45 seconds. Don't cheat. Okay. Nice. Yeah, what was that? Okay. Again, in API recommended procedure, cement should be added to water no more than 5 seconds, 15 seconds, 20 seconds, 35 seconds. In API recommended procedure, in which RPMs do you mix the cement? Yeah. 15 seconds, that's 4,000, and 35 seconds, that's 12,000 RPM. What kind of cement I used in my studies? Easy one. Class A. Yeah, okay. Yes. What was the mixing ratio of Class G cement with water? 38% by weight, 40, 48, 44. Okay. Three different mixers I used in my studies. Which one was not one of them? Susan, you're on fire. You can select multiple choices in this one. Which criteria I followed in the scaling up of mixing process? Keeping the SME same, multiplying all parameters by constant factor, dimensionless analysis, all of them. Yes, okay. Which parameter did Paget guy suggested as a improvement for SME concept? Viscosity, volume, impeller RPM, or shear rate? In the dimensionless analysis, which one of the dimensionless numbers below were used as the scaling up criteria? Okay, last one, bonus question. Who was the quote from in the last slide of the presentation? There's a hint. Yes, Tiger Woods, the golf player. Okay, that was all. And there's a poll coming. Did you enjoy it, today's session, or not? Yeah. Thank you. Okay, let's see who is the winner. Third place, Nico.
Nico.
Marina. Yes, Eileen. Here or?
Yeah.
Yeah.
Yeah, it's good to go.
The distance, congratulations. Okay, thank you all again for coming to my lecture.